Okay, let's continue the lecture on data inference. In the previous lecture, we talked about sampling distributions and the central limit theorem and the ideas behind it. And now we're going to continue to look at statistical inference, meaning that after we have the parameters from our sample, how do we actually use those parameters to say something about our population as a whole? Now there are basically two approaches here. The first one called estimating parameters, or just estimation, and the second one, which is the one which most likely you'll be using most often, is hypothesis testing. Now both of these, as mentioned earlier, form kind of like the core idea behind how you're going to use virtually every statistical test from now on. Let's start with estimation, or so-called point estimates. The idea here is to estimate population parameters from sample parameters, and this is going to answer the question that's been nagging at the back of our heads, which is up till now. When we gave questions about sampling distributions, it was always of the form like you are given the population mean equals what? You're given the population standard deviation equals something. From these two values and given sample size of whatever, what is the probability that when you go out and collect a random sample, you'll get a sample mean of something, something, something or the other? Now that's all fine and good. The problem is that if you already know your population mean, what's the point of doing inference in the first place? Remember, inference, statistical inference, says that I collect a sample from unknown population, and from that sample I want to say something, I want to infer something about the population. So in other words, most of the time when you do your research, the population parameter or the population mean is unknown. All you have is the sample mean, right? So you got to use that sample mean to say something about the population. So that's what estimation is about, or these point estimates here. So in other words, let's say you have you want to find out about proportions. You want to know what's the population proportion, or pi, and you estimate the population proportion from the sample proportion p, or you estimate the population mean mu from the sample mean x bar, or you estimate the population standard deviation sigma from the sample standard deviation s. Now just mention here that despite all these, we are mainly only going to use this one, meaning we are mainly only going to be estimating the population mean using the sample mean. Now the method we use is called confidence intervals. Now we are mainly working on continuous distributions, so these confidence intervals are interval estimates of probability, meaning we calculate in terms of, for example, the probability of x greater than 10. So we calculate ranges, we calculate intervals, as opposed to point estimates. For example, probability of x equals to 10. Now point estimates, just a reminder, they only make sense for discrete distributions. But again, we are mainly working on continuous distributions here, for example, the normal distribution. Now, bear with me for a while about confidence intervals while I cover the points about them, and we'll explain more about what they actually are. Now, the ends of confidence intervals are also called confidence limits. For example, this x greater than 10, now the actual interval is everything from 10 and above. But the value 10 here, or in this case the value 5 and 15 here, these are the ends of the confidence intervals. They call confidence limits. Now, so the confidence interval is actually just this range from one number to another, the value between something to something. For example, let's say I'm calculating the heights of students in University of Malaya. So these heights in centimeters, and two of these values here, let's say 100 and 150, so I would say interval between 100 cm to 150 cm, that's a particular interval. And for it to be a confidence interval would be saying that between these two confidence limits, this particular range, this particular interval, this confidence interval, there is a particular probability, usually 95%, that within this interval lies the actual true population mean, or mu, right? Let me repeat that. What a confidence interval means is that I define a particular interval from one number to another. Okay, now maybe this time let's consider weight. For example, what is the average weight of all men in Malaysia? Now I do not know the actual weight, the actual average weight of men in Malaysia. That would be the population mean, mu. Maybe the population mean, the actual population mean is, let's say, 80 kilograms. I don't know. But when I calculate out a confidence interval, I'm saying a range. I'm giving a range. I say the population mean of the weights of men in Malaysia is somewhere between, let's say, 50 kilograms and 100 kilograms. And I'm saying I am 95% sure. It doesn't have to be 95, it could be another value. I'm 95% sure, or I'm 90% sure, or I'm 99% sure that the actual population mean, the actual population average of weights of men in Malaysia lies between the values of 50 kilograms and 100 kilograms. And that is my confidence interval. Okay? Now, how do I actually calculate this particular confidence interval? How do I calculate the confidence limits? I calculate them based on my sample mean, right? So this is answering the question. This time I do not know what the actual population mean is. I only know the sample mean. So only given the sample mean, I now calculate a confidence interval that tells me something about the population mean. I still do not know what the actual population mean is, but I have some idea. I'm roughly 95% sure, I'm 99% sure, I'm 90% sure, I'm 80% sure that the actual population mean lies within this particular range, called the confidence interval. Okay, so that's what a confidence interval is. Now let's look about how we actually calculate this confidence interval. Now, as with many things in statistics, how you actually calculate it turns out to be something quite simple mathematically. Right? It's actually just simple algebra. However, just like everything in statistics, what is simple mathematically, the hard part is actually understanding why or how the whole thing actually works. Right? So, to understand how these confidence intervals are calculated, let's start off with what we've been doing all along, which is we have a sampling distribution, right? And we know that the middle of the sampling distribution, or the mean of the sampling distribution, is x bar bar, or the mean of all the sample means, and x bar bar is also the population mean, mu. Okay, so we know that for now. Now let's pretend that we are trying to calculate what is the area in between the area plus minus mu that will give me 95% of all sample means. Okay. Now it doesn't have to be 95%. Usually confidence intervals are you're asked to calculate the 95% confidence interval, but it doesn't have to be 95. It could be 90. It could be 99. Right. And if you know how to calculate 95% one, I'm sure you know how to calculate the rest. But let's stick with 95% for now. So you're asked to calculate what is the values of z down here that will give you 95% of all the sample means. So if you work it out, you can get a simple formula like this. So the probability where z lies in between these two values, these are z values by the way, equals 95%, right? Or 0.95 probability. This is the area underneath the curve in between the values negative 1.96 to positive 1.96, and z, these are the z values, right? Now, why is it 1.96 here, positive and negative 1.96? Is because 1.96 z plus minus z 1.96 gives me exactly 95%. If you remember, one of the rules of thumb we heard was that the mean plus minus 2 standard deviations gives you about 95%. Okay, the reason we say it's about 95% is because it's not exactly 2. It's not exactly 2 standard deviations. It's 1.96 standard deviations. Okay. Now, with that in mind, let's expand this equation a bit. Z here, what is z? Z is actually x bar minus mu divided by standard error, which standard error in this case is standard deviation divided by square root of n, right? This one, we've done it many times already, so I'm sure you all remember where this came from. Remember, mu here is actually x bar bar, but they're one and the same thing. So this jumps to this, no problem. Now the final step here is just a rearranging of this. You rearrange it such that mu now lies in the middle, and you've pushed x bar out. Okay? Now notice what this means now. It changes that says that mu, or the population mean, which is something I do not know, lies in between this number and this number. And these two numbers here, hint hint, these are the confidence limits, and the range from this number to this number gives me the confidence interval. Confidence interval of what? Or it is 95%. What does that mean? That means in between these two confidence limits, this confidence interval, I have a 95% chance that the true population mean lies inside it. Okay? This is where the whole thing works out. It says that what is the population mean? I do not know. What do I know? I only know the sample mean. But from the sample mean, I can give an estimation about what is the actual population mean. I still do not know what's the actual population mean, and I will never know unless I count all the individuals inside the population, but now I can have an estimate. I'm 95% sure that the actual population mean lies between this number and this number. Now notice, what is actually this? What are actually these confidence limits? This is actually x bar sample mean plus minus 1.96 times standard error. Okay? X bar plus minus 1.96 standard error. What is the standard error? The standard error is just the standard deviation of the sampling distribution. Or in other words, it is one particular mean plus minus a certain number of standard deviations. Okay? Now you may look at this and you may think to yourself, this looks very similar to what we said earlier, the beginning part, which is mu plus minus 2 standard deviations. What's the difference between the two? What's the difference between me putting mu plus minus 2 standard deviations and now this standard error plus minus, let's call this about 2 standard deviations, or standard errors in this case. Now the difference is, when I did it as mu plus minus 2 standard deviations or standard errors, what that meant was in between this range, I can find 95% of the sample means. Okay, when I put mu plus minus 2 standard errors or 2 standard deviations, I'm saying that in this range I can find 95% of the sample means. Now when I reword it like this, I'm saying from x bar plus minus about 2 standard errors here, x bar plus minus 2 standard errors, in this range I'm 95% sure I can find the actual population mean. There's only one population mean, so I'm not saying that there lies 95% of all the population means because there's only one of them. I'm saying there's 95% chance the actual population mean lies within this range. Okay, now they look the same. It's still something plus minus something about standard error or standard deviation. However, their meanings subtly differ. Okay, I repeat that one last time. When you have earlier, you did this kind of mu plus minus 2 standard deviations or 2 standard errors. What that meant was within this range lies 95% of the sample means. When you do it like this, x bar plus minus about 2 standard errors, I'm saying within this range, I'm 95% sure that the true population mean is somewhere within there. Right? Now again, it doesn't have to be 95%, it could be 99%, it could be 90%, it could be 80%, up to you. When this changes, the only thing that changes is this number. Okay? The only thing that changes when you change this is this, which is the Z value. Got it? Or this one, or this one. Alright? They're all the same. Now, just a quick note, one thing you might have noticed is that now I've solved the problem of the unknown population mean. Right? I'm estimating population mean based on what I do know, which is my sample mean. And of course I do know what is my sample size. But I've cheated slightly and I've been assuming that I know the population standard deviation. How do I deal with this? Just quickly, for now, I'm just going to say that when we put population standard deviation here, we actually just replace that with sample standard deviation, meaning we just put S here, right? We're kind of assuming that S is the same as sigma in this case. It's not exactly the same, but the mathematicians and the statisticians have worked out and said that for most intents and purposes, you can replace sigma here with S. Okay, so there's a slight cheat here. We're not exactly estimating it purely from everything we know. We are still doing some kind of little tricks here. Okay, now the idea here where S is equivalent to sigma, we'll come across some situations later where it's not necessarily true, and we'll talk about how we can change the way we do things at that stage. Alright, so don't worry too much about this just yet, but just something to keep in mind in case you suddenly noticed and says, hey, wait a second here, there's another population unknown here which we haven't actually dealt with. Now a quick checkpoint. We are given the mean level of alcohol consumption in 142 men with psoriasis. Now this is just a chronic skin disease. Don't worry too much about it. Just assume it's just a particular condition for now. So we have a sample size where n equals 142, right? The group mean is 42.9 grams per day with standard deviation of 85.8. Now notice this is the sample mean and this is the sample standard deviation. Okay, this is x bar and this is S. Question: how precise is this estimate of the mean alcohol intake? Or in other words, what is the 95% confidence interval for the true mean? Or what is the 99% confidence interval for the true mean? Right? How do I use these values here to estimate what is the true average, true population mean level of alcohol consumption in men with psoriasis? Okay, that's the true mean. The true mean is for all men. What is their, all men with psoriasis, what is their mean level of alcohol consumption? Now, of course, the idea here is you're trying to link alcohol consumption with this particular condition. But let's not worry about that for now. So let's work for the 95% confidence interval. So pause for a moment, give it a try, and then we'll continue. Okay. So if you follow the formula over there, which is you changed it into this particular format here. Since we're only working for the 95% confidence interval here, so Z value here is 1.96. As mentioned, sigma here, you just replace it with S, so standard deviation will just be using 85.8 here, and becomes 142. Mean value here is 42.9, and you should have gotten this particular result, or this particular confidence interval. If not, check your numbers again. Now in the previous confidence intervals or the estimations, what we're basically doing is we're trying to estimate the true population mean based on the sample mean, right? Based on the sample mean, which is data I collect, can I say something, can I infer something about the true population mean? Well, that's quite useful, but most of the time when we do research, we're actually interested not just in coming up what is the true population mean, but actually in comparing the samples we have with something else. Now, for example, in this, let's go back to the previous one. Investigators studied 142 men with psoriasis, found a mean alcohol intake of 42.9 grams per day, right? Up to this part is still the same. We have this sample group of 142 men. But then we continue. Now, is the mean alcohol intake of psoriasis patients different from that of the non-psoriasis skin disease patients? Or in other words, on average, do men with psoriasis drink the same amount of alcohol daily as men with non-psoriasis skin disease? Or whatever control group that I'm comparing to. Now, what is the whole idea behind this thing? The whole idea is I'm trying to make a hypothesis, or I have a theory. I have a theory that says that this particular skin disease has something to do with the mean alcohol intake, right? Now, if that is true, then when I make a comparison of the group of people with this particular skin disease compared to another group of people who do not have this particular skin disease but may have something else related, but not this specific one, right? Then there should also be a difference in the mean alcohol intake. Okay, so I'm looking for a difference. I'm looking to see whether the mean alcohol intake of this group and this group, are they different from each other? And if they're different, that tells me something. That tells me that maybe, possibly, this particular skin condition has something to do with the alcohol intake, right? That is the idea here. So now I have the sample mean over here of this group that I'm testing, the psoriasis group, and I have the sample mean. So the sample size and the sample mean, and I'm going to compare to the control group. And I assume here that the control group has a population mean of 21 grams per day and a population standard deviation of 34.2. Now notice here I'm giving the population values again, and as you can probably guess, in the future you also see how to do hypothesis testing where I'm comparing two sample groups with no population mean, right? That's possible as well, but for now let's just work with this simpler case for now, where I'm just comparing one sample, right, with a known population mean and population standard deviation. Okay, and the question now is this sample different from this population mean? Hypothesis testing involves a series of steps that you have to go through, and these steps are a methodological way in which you are going to test your hypothesis or test your theory. And these steps, they kind of enforce a particular way of thinking, right? A particular statistical way of thinking, which tends to be a bit less intuitive if you're not used to it. Compared to estimation just now, although some of the steps took a bit of thinking about it, but I feel that estimation, for most people, you tend to accept it. You understand the ideas behind it. Hypothesis testing tends to be a little less intuitive than that, and so requires a little more thought, but still, please try to understand the ideas behind it, and it will make things a lot easier. Now, in a nutshell, what do we do? First, when we want to do hypothesis testing, we start by declaring the null hypothesis, which states there is no effect of difference between the samples. Now let's go back to the example we gave just now. We're comparing mean alcohol intake between between psoriasis patients and non-psoriasis, or skin disease or this particular condition with those without that particular skin condition. Now you might be expecting that I am trying to find a difference. In this case, I actually start by saying, what if there is no difference? Or in other words, I'm saying that as far as mean alcohol intake is concerned, mean alcohol intake is totally independent from whether you have this skin condition or not, right? There's no effect on mean alcohol intake whether you have this skin condition or not. Or in other words, to put it yet again, those people who have this skin condition, their mean alcohol intake should also fall within the same kind of population distribution as the people who do not have this skin condition, right? As far as mean alcohol intake is concerned. Okay? Now, I'll talk about that in a moment, but let's continue for now. Evaluate the probability of obtaining the observed data if the null hypothesis were true, right? Now this means that if the null hypothesis were true, that means the patients with this skin condition and the patients without the skin condition, they come from the same population, because there's no difference between them. So they come from the same pool. So if that is true, I have just gone out and collected a particular sample. So I know an X bar here, right? Now, what is the probability that if my skin condition patients came from the same population as the one without the skin condition, what's the probability of me actually collecting this X bar? Now, let me give example from the earlier days. This is equivalent to me asking if I have a population that I know, let's say the heights of men in the hospital, okay, and I know the mean height of all the men is so much, and the standard deviation of their heights is so much. What's the probability of me finding a person that is, let's say, taller than 2 meters, for example? Okay, now you can calculate that easily, right? Because you have the population distribution, you know the mean, you know the standard deviation. So I'm asking you, what's the probability of you finding a person, going out and finding a random person with a mean of taller than where a person who is 2 meters or taller, and you can calculate that easily. Now the same idea here is applies. In this case, you have a population distribution, okay, and you are assuming, remember, by your null hypothesis, you're assuming that your sample, which it comes from this population of patients who have this skin condition called psoriasis, and there's another population comparing to, which is these people who do not have the skin condition, right? You're comparing their mean alcohol intake. Now your null hypothesis states that I assume that these two, there are no difference between them, or in other words, they are one and the same. If they're one and the same, that means they come from the same population, right? So in other words, the population parameters, the mean, the mu value, applies to both not both samples, applies to both populations because they are the same. And the standard deviation applies to both populations because they are the same. Now, if that is true, if the null hypothesis is true, then I have just gone out and collected a particular sample, and the sample mean is x bar. So it'll be like saying, what is the probability of me, given these population parameters, going out and finding the sample mean of this value and greater, or this value and smaller, right? This of course comes from the sampling distribution, which you can calculate from your population parameters. So this here is to evaluate the probability of obtaining the observed data if the null hypothesis were true. Okay, so assume null hypothesis is true. What is the probability of me collecting this x bar and greater or less? Okay, now when you calculate the probability, you get a probability value. Let's say the probability was 0.03 or 0.5 or 0.001 and so on and so forth. Now we have to decide a threshold. A threshold of we call the p-value threshold, and we decide whether or not the null hypothesis has to be rejected, meaning this original assumption that I made where these two populations were actually one and the same. Now, if the probability which I calculated here exceeds the threshold that I have set to reject the null hypothesis, if it exceeds this, then I say that null hypothesis is no longer true. I reject it. And if I reject my null hypothesis, I'm basically saying that yes, there actually is a difference between this population of psoriasis patients compared to the population of non-psoriasis patients. So stop for a moment, pause for a moment, and think about this for a while, about this idea about what hypothesis testing is doing. And then when you feel like you've gotten it, we'll continue on a step-by-step basis about how we actually carry it out. Now let's try to carry out hypothesis testing step by step. As mentioned previously, the first thing we have to do is to state the research question, or the theory that we are testing. The correct term here is the null hypothesis, or H0. Now the null hypothesis has to be stated in this form, where there is no difference between the hypothesized value and the population mean. Or in other words, there's no difference between the value, the population mean of the group that we are testing versus the population mean of the other one. Or in other words, we are saying that these two come from the same pool. They are the same. They come from the same population, so they have the same population mean because they are one and the same thing, because there's no difference between them. Now if we have stated our null hypothesis, we continue to state our alternative hypothesis, or H1. The alternative hypothesis is the exact opposite of the null hypothesis. So if the null hypothesis says there's no difference between these two groups, then my alternative hypothesis says that there is a difference between the two groups. I am saying that this sample which I collected came from a different population, or it came from a population with a different population mean compared to the control one which I'm comparing to. Right? Now, given one hypothesis, the null, and given the alternative hypothesis, H1, we continue on with the hypothesis test, all the rest of the steps, calculate out the Z values, P values, and so on and so forth. Then I have to come out and give a conclusion. And the conclusion is usually based on the calculated P value. You will see how to do that in a moment. But just a quick example, usually we state a cutoff point. Let's say we say I am going to reject the null hypothesis if the cutoff point goes below with a cutoff point of 0.05, right? Then when I actually calculate P, I calculate P equals 0.01, therefore P 0.01 is below P 0.05, which is below the threshold of my cutoff, and I conclude that I reject H0. I reject the null hypothesis, meaning I'm rejecting this hypothesis here, and therefore I have to accept the alternative hypothesis. So I'm saying that based on my hypothesis test, the null hypothesis has been rejected, it's false, and the alternative hypothesis is the correct one. So therefore I'm saying that yes, there is a difference. It does come from two different populations, or the two population means are not equal. Now alternatively, I could also come to the conclusion where my p-value which I calculate does not go below the cutoff value which I set. Let's say I was 0.05 and I calculate that p is 0.1, right? That's much greater. So when I get a value like that, my conclusion then becomes the null hypothesis is not rejected. Okay, it is not I do not reject the null hypothesis, and therefore I'm not saying that this is wrong. Now notice when I say that the null hypothesis is not rejected meaning could be true, right? I'm not saying that the alternative hypothesis is wrong, right? Not rejecting H0 is not the same as rejecting the alternative hypothesis. Or in other words, not rejecting H0 is not the same as saying H0 is true. Now notice there's a subtle difference here. I'm just saying that I don't have enough evidence to prove that H0 is false. Now there's a subtle difference here. This is not the same, I'll just emphasize it once again, not rejecting H0 is not the same as saying H0 is false. I'm just saying that I do not have enough evidence at this stage to say that H0 is false. Or in other words, H0 is never accepted. This is not a proof that H0 is true. If you want to prove that H0 is true, there's a whole different series of tests that you have to do, and they have nothing to do with this. Okay, so keep that in mind. So let's translate that into actual steps. Based on the example previously, our H0 or our null hypothesis, we are saying that the sample mean from the group that we've taken, the group with the skin disease, we are saying that they come from the same population as the group with no skin disease, and therefore they come from the same population, so the population mean is the same, and the population mean was given to be 21. So I'm saying here that my psoriasis population mean is also 21, right? So equals 21. If this is the null hypothesis, then the alternative hypothesis is of course the opposite of this, and the opposite would be the mean is not 21 grams per day, right? So we're saying that the mean alcohol intake is either yes, they are the same, or no, they are not the same. When I put it this way, where it's either yes or no, this is what we call a two-tailed or non-directional test. Observations may occur in any direction, meaning I'm saying there's a possibility that when I actually test, when I go out and measure my sample mean, it could be far greater than 21, or alternatively it could be far less than 21. It could go either way. And if it's much greater or much less, either way may give me cause to reject the null hypothesis. Now if I expect, if my experiment is set in such a way that I expect the sample that I'm testing to be only in one direction, meaning I expect it to, the possibility is almost 100% that it's either the same or it is far greater. Let's say it's only one direction, it's never going to be less, then I can do an alternative test. It's not very different, it's just a difference in the way that it's stated, and we call it a one-tailed or a directional test. So in that case, then the alternative hypothesis means we are expecting it to be much greater, so it will be mu is greater than 21 grams per day, and so the null hypothesis then would be mu is less than or equal to 21 grams per day. Alright, so instead of equal and not, it will be less than or equal and greater than 21 grams per day. Now the rest, whether it's whether it's two-tailed or one-tailed, the rest of the steps actually are about the same. The only difference comes in how you calculate whether it is significant, whether it is significant enough to reject the null hypothesis or not. And we'll look at examples of that in the future. Just that keep in mind that a one-tailed test tends to make it easier to prove for statistical differences. And because of that, you need to justify why you are using a one-tailed test. Right? You have to have good justification for why it is simply impossible or unreasonable that there could be such a possibility that the value that you're testing could be lower than 21. must always be higher, and so the burden of proof is quite high. So to keep things simple, just stick to two-tailed. Then you don't need to worry about it. Then we decide on the appropriate test statistic. Now so far in our case, we've only been using one type of test statistic, and that's the Z test statistic, also known as the critical ratio, which is based on the Z distribution, blah blah blah. Now there are many other test statistics that we'll come across in the future. The most related one being the T statistic from the T distribution. Later you also come across the F1 or the chi-square one, and so on and so forth. Now, how do we decide what to use? Well, it depends on the situation. We'll look at the T distribution pretty soon, but I'll just mention that the Z and the T distribution are actually very, very similar to each other. Just that the T distribution considers a bit more stuff. Right? So in real world situations, you tend to use T more than Z. For example, right, again, we'll talk about the T distribution in more detail in the future. But remember, we said that we are making a shortcut. We says that in the estimation stage, we say that we do not know the population mean, and then we calculate the confidence intervals. But there was a cheat there, and that's our calculation made use of the population standard deviation, even though we didn't really know it. All right. So the T distribution actually takes that into account. It says that if you do not know the population standard deviation, and all you know is S, which is the sample standard deviation, most of the time this is actually true, then the T distribution actually takes that into account. It adds a bit more variability compared to the Z distribution. Now we continue by selecting the level of significance, or the alpha value, this alpha here. I also called it by different names just now. I called it a cutoff value, I called it threshold value. But basically, what actually is alpha? Alpha is a probability value. Now alpha, by tradition, usually is set to 0.05, although sometimes you also see 0.1, or more commonly 0.01, or even values below that. Now, when this 0.05 is actually a probability value, it represents a probability of 5%. Before I explain what actually it is, first let me just have a quick jump to calculate what is the p-value. P-value is something we calculate out. Alpha value is something we state. I state that my alpha is 0.05, my level of significance. My p-value, however, I calculate based on the sample parameters which I measure. Right? Now the p-value here, after I calculate, is what it means is that it's the probability that the observed result that I obtained in my measurements in my collected sample is due to chance alone. Okay? Now, what does this actually mean? What it actually means is this p-value, it sounds a bit convoluted, but we've actually been doing this again and again and again. Now, basically it just means that if the null hypothesis is true, based on the null hypothesis assumptions, I collected a sample, correct? And I said that the sample comes from the same population as the control population that I'm comparing it to, correct? So that means they come from this same population distribution that's equal to that of the control, which I am comparing to. And I know inside this population distribution, I know the mean, I know the population mean, I know the population standard deviation, and therefore from there, if I know the sample size, which of course I do know, I can then derive out the sampling distribution. Now the sampling distribution obviously has the same population mean and has a standard error inside there. Now based on all that, I then go out and collect a sample using the sample size which I've defined. And from there I have a sample mean. Let's say I get a sample mean, let's say my population mean is 50 and my sample mean then is 30. Okay, that means that 50 in the middle, 30 over here. Then I calculate, then this is equivalent to me asking what is the probability for the p-value, what's the probability of me obtaining this 30, this value of 30, assuming that the null hypothesis is actually true, meaning that assuming that it comes from a population where the population mean is 50, right? Now, it's a slight difference. Of course, you cannot calculate probability at one point, you're calculating the range. So it's like, what's the probability that that I could have gotten this sample mean of 30 all the way from negative infinity to 30, this particular area underneath the curve. Now, this will be a one-tailed one. For a two-tailed one is what's the probability of me getting a negative 30 or a positive 30 at the same time. Right? I know it's very strange since you actually collected since you actually collected 30 here, but based on two tails, what we are trying to question is what's the probability of you collecting this particular value or something even more extreme, whether it was less or whether it was more. Alright? If the assumptions of the null hypothesis were true, meaning that they come from the same population distribution. So that's what the p-value is. It's just another of your exercises, which is calculating the ranges of the area underneath the curve. Right? In this case, for two-tailed, based on your sample mean, you calculate here and here, or let's say it was here, then you also calculate here, you calculate the area here, you calculate the area here, and that is your p-value. So it's the probability that the observed result is due to chance alone. Chance alone because they were based from the same probability distribution, so just by pure chance you could have gotten here, 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 but obviously the further to the tails you go, the less likely it will become. So your p-value, the further you go, you move away from the mean, right? Your p-value is going to get smaller and smaller and smaller, right? Or in other words, it's less and less likely that the observed result that you got from doing your measurement is simply due to chance. Much more likely, the observation that you get, if it's very, very unlikely, is not due to chance, it's because your assumption is wrong. And what was your assumption? Your assumption was they come from the same population distribution. Or in other words, they are not from the same population distribution, or in other words, they are actually different. Okay? They are significantly different. So, quick repeat again. What is the p-value when we calculate? The p-value is the probability of obtaining a result as extreme or more extreme than the one observed. Or in other words, if I calculated 30 when the mean is 50, or if I calculate the sample mean of 80 when my mean was 50, then I have to calculate out the p-value of the range from negative infinity to here and here to positive infinity for two tails, and for one tail is just negative to here or positive to positive infinity. Okay? And that will be the area underneath the curve. And that would equal to be the probability that the observed result or anything more extreme is due to chance alone. Okay, so then what is the alpha value then? The alpha value then just says that after I've calculated p-value, then it just says that, alright, p-value as you go further and further away from the mean is less and less likely that it's simply due to chance. Where do I cut off? Where do I cut off and say that it can't be due to chance? It must be because your assumption is wrong, meaning the null hypothesis is wrong. So by tradition, we've set it at 5% or 0.05. It so happens that this also means that this is the probability of incorrectly rejecting the null hypothesis when it's actually true. Meaning, assume that the null hypothesis was actually true. Assume that it actually does. The two means actually are the same. They actually do come from the same population. And when I collected a sample mean that was very small, it just so happened that it was totally random. I just so happened to pick a sample that happened to have a lot of low value individuals, and therefore it so happened that the sample mean was very far from the population mean. But actually, then our hypothesis was true. If I took another sample, maybe I found out that the new sample is much closer to the population mean. So that's what alpha is. The 5% here says that most of the time, or specifically 95% of the time, if the p-value I calculate goes below my alpha value, it's going to be true. Right? My conclusion of rejecting null hypothesis is going to be true. But 5% of the time, if I say that I reject the null hypothesis because the p-value I calculated goes below the alpha value, then it's actually wrong. It's actually wrong. It so happened that it really was simply due to chance that the p-value I calculated was too low, below the alpha. Now obviously, if I want to be more confident, I can set my alpha smaller. Instead of 0.05, I can set it 0.01. Then my probability of incorrectly rejecting the null hypothesis when it's actually true is now 1% rather than 5%, and so on and so on and so forth. As mentioned previously, by tradition, common alpha values or cutoff points or thresholds or whatever you want to call it is 0.05, or in other words 1 in 20, or 0.01, or 1 in 100. Interpretation. After I calculate my p, if my p is smaller than my cutoff, which is, let's say, this one, we call it statistically significant. If P is much less than my cutoff, we call it highly significant. Or if P is greater than our cutoff, we just say it's not significant. Right? Now, what is less? What is the threshold for less before we call it highly significant? Once again, it differs among people. But so far, I've noticed most people say that if it's below 0.05, then we say statistically significant. If it's below 0.01, then we call it highly statistically significant. But that again, that depends upon the field, and it depends upon the different journals and so on and so forth. But no one's going to scold you if you just use 0.05 because that's the accepted standard. Okay, continuing then, there are two ways we can approach it. We can approach it by first calculating the test statistic, and from the test, meaning the z-value or the t-value or whatever, and from that test statistic we convert it into a p-value, and we convert that p-value to the alpha value that we have defined, and then we see whether it has it's in the reject region or it's in the not reject region. Okay. Alternatively, we go backwards. We set our alpha value to be 0.05, and from the alpha value we go backwards and say this alpha is equivalent to a z value or a t value or whatever, or a z value of particular number, and then we say that then my calculated z value has to be either above or below this particular z value. Okay, they are actually one and the same thing, but the reason we have either this approach or that approach is because it depends upon the tables we were provided. For some tables, because there are too many variables that could affect the distribution, they can't give us like the z table where there are many different values for z. Instead, they only give a few critical values, like what is the value for this distribution when alpha is 0.05. What's the value for distribution alpha equals 0.01, stuff like that. So in other words, they're asking you to compare based on your test statistic rather than compare based on your p-value. However, they are one and the same. Just remember that the test statistic can be converted to a p-value, the p-value can be converted to a test statistic, and vice versa. Right. Let's, however, assume for now that we have calculated the p-value. Right. So, where do I draw the line? When I say a p-value of 0.05 here, or in other words, the alpha value, this is my alpha which I'm comparing my p-value to, where do I actually draw the line? When I say alpha of 0.05, I'm actually saying there is a 5%. There's a 5% possibility that it could go beyond either this value or this value, and it's two-tailed. So in other words, there's a 5% chance it could go this way or this way. If I'm being fair, that means equal odds to either this way or this way. So if 5% here, if these two ends add up to 5%, that means there's a 2.5 area of rejection, 2.5% area of rejection on each end. This is for a two-tailed test. So in other words, my alpha value, or my defines a cutoff here and here at the negative 2.5% and the positive 2.5%. And if the p-value that I calculate based on my sample mean goes beyond these two cutoff values, then it's in the rejection region. I'm saying that I found a statistical significant difference, I reject the null hypothesis, etc., etc. That's for p-value of 0.05. Now this is for two-tailed. If it was one-tailed, same thing, except whether I decide, let's say I'm looking only at less. Because there's only one tail I'm concerned with, I'm saying there's a 5% chance total, and because there's 5% chance only it goes in one tail, so I'm saying that it's entirely here. There's exactly 5% only on this one tail, and then my or my alpha value is here, and if my p-value goes beyond that, then I reject. If it doesn't go beyond that, I say not enough evidence to reject, and so forth. Right? So that's the difference between a one-tailed and a two-tailed. We'll look at a picture of it in the next slide. So as mentioned, here is a picture of a distribution. This is a standard normal distribution, or the Z distribution. For alpha value equals 0.05, both of these are for alpha values of 0.05, except this for two-tailed and this for one-tailed. What does it actually mean? Alpha value 0.05 means there's 5% chance of it occurring, of extreme values occurring totally by chance, either on the positive or the negative. So to be fair, you split them up, so it's 2.5% here, 2.5% there, and it's the middle 95% here. Right? So, sorry, it shouldn't be called the acceptance area, it should be called the not rejection area. Except, I guess that sounds bad. Anyway, so the Z value, the threshold that I'm aiming for, is either negative 1.96 or positive 1.96. Okay, so if the Z that I calculate either exceeds 1.96 or goes below negative 1.96, rejection. In comparison, for one tilt, I'm now saying that 95% is here and 5% is here, or it could be the other way around. Bottom line being there's only one tail this time, and this is the rejection area. Now notice the number or the threshold that I'm aiming for now has changed. It's now 1.645. You can calculate inside your tables that if you take this and then you calculate what's this plus over this, and you'll find out that yes, this is actually 95%. I'm sorry, it should actually color all the way to the end, to infinity. Just an accident over here. Now, so rejection area is here, and this is the non-rejection area. Now notice there's one slight problem, which is that if my Z value, which I calculate, exceeds this, let's say I got Z value of 1.7, I'm in the rejection area, fine and well and good. But if it so happens I got a Z value of negative 3, which is very, very far out. I'm not actually in the rejection area, I'm in the non-rejection area. And that doesn't really make sense, because it shouldn't be there. Which is why you have to justify using a one-tailed test. Because it actually, if you use a one-tailed test, based on the assumptions you're making, you can end up with a situation where you have a sample mean which is really different from your population mean, but because it's in the wrong direction, your test actually doesn't pick it up. After all that preparation, now it's finally time to perform the calculations. So, the mean daily alcohol intake for this psoriasis skin condition patients was 42.9. I'm comparing to population mean of the non-psoriasis skin disease patients, where it's 21, and the standard deviation is 34.2. Wow, looks like a very big difference. But then again, the standard deviation is also very big. How do I go about it? Simple. Calculate Z value. Z equals the sample mean minus population mean divided by the standard error, and here is my final Z value. Now what am I going to compare to? If you remember the distribution diagram that we showed just now, for an alpha value of 0.05, two-tailed, then the Z value that we are targeting is something like either positive 1.96 or negative 1.96. Meaning if we exceed that or we go below that on the negative, then we reject. Right? Now obviously here Z value of 7.63 falls way into the rejection region. Therefore the null hypothesis is rejected. Now remember, we could have done this the other way. We could have converted Z into a p-value and compared the p of this one, the p of this particular Z, with our alpha value of 0.05. But you will notice, if you try to do this inside the lookup table, 7.63 is way off the charts. Right? It's a tiny p-value. So therefore, it's good to know both ways to do this, either through the p-value way or through the test statistic way. So, what's our conclusion? Our conclusion, on average, men with psoriasis consume alcohol at levels different from 21 grams per day. Now notice, I'm not saying they consume alcohol at levels more or less than 21 grams per day, because I did not test for that. I tested to see whether it is same or not same. Okay, and based on my tests, based on the statistics, I have concluded that they are not the same. They are different. They're statistically different. I have rejected the null hypothesis. Now, if you're doing the p-value method and you have a computer with you, you can end up with as accurate p-values as you want. So when you do that and you end up with p-values which are tiny, you just report them as p equals less than 0.01 or p equals less than 0.0001 or so on and so forth. Up to you. Usually I just use this. Anything below that is just academic. Now what happens then if you have something that's kind of like on the borderline? P equals 0.051. So strictly speaking, based on the alpha value, you should just conclude there's not enough evidence to reject the hypothesis. But in practice, usually upon getting figures like this, we usually go back and we test to see whether our data is actually correct. Did we make any mistakes? Alright, and maybe we can improve this result somewhat simply due to finding out some mistakes which we made. Or more likely, we just report this and we say that, however, because the p-value is such borderline, it is quite possible that if we collected more data, we'll be able to change this from a not significant to maybe a significant rejection. Or in other words, a different conclusion might have been gotten if we had simply collected more data or performed a better experiment. Now let's try it out for ourselves. So a study is done on a group of PBC patients. We compare them to a published mean where the serum albumin is 33.5 grams per liter. Sample size 216. The sample mean which we collected based on our group is 34.46 grams per liter, and the standard error of the means, very good, it's been given to us, is 0.397. So test it out, and keep in mind, try to do all the steps, meaning start off with the setting out the null hypothesis, alternate hypothesis, alpha levels, so on and so forth. Usually if they don't say anything else, assume alpha of 0.05 and two-tailed. Okay, so the first step was for the null hypothesis. Null hypothesis means there is no difference, or in other words, the mean serum albumin in all PBC patients is similar to the published mean serum albumin, meaning they come from the same population distribution, or in other words, they should be the same. Their mean value should be 33.5, and so the alternative hypothesis then it is not 33.5. Calculations, z equals the x bar, or the sample mean, minus of the mu, which I'm comparing to, divided by standard error, and we get this 2.42. And going by, as mentioned, you could calculate it based on z, or you could calculate the p-value. Either way works, but your conclusion obviously then should be rejection. Right? In other words, we reject the null hypothesis. Yes, there is a significant difference because this is lower than the alpha value, or alternatively, this z value of 2.42 is higher than our target of 1.96. Now, just some quick points of note I should point out. We've introduced the alpha value. Now, this alpha value is also known as something called a type 1 error. And just a quick reminder, this, when we define the alpha, what we actually mean by it is this is the probability of rejecting the null hypothesis when there is no difference. Okay, when such an error actually occurs, where we accidentally rejected the null hypothesis when actually there was no difference, the null hypothesis, in other words, the null hypothesis was actually true, right? Then we call it a type 1 error. And if we set the alpha to a low enough value, this should be quite rare. So if we set alpha of 0.05, we should only expect this to happen only 5% of the time. So as mentioned, if this condition actually occurs, it is a type 1 error, and also known as a false positive. Okay, in other words, we found a positive result, positive to us, in other words, statistical, we got a positive statistical result, when actually the correct answer was a negative. Right? Now there's an opposite kind of error, or not to say opposite but related one, which we call a beta, or a type 2 error. Now we accept, we don't really accept, shouldn't really be accept, but we do not reject the null hypothesis when actually there is a difference. Alright? So in other words, we carried out the data and then we got a p-value, or calculated p-value, but because of our alpha, it wasn't we didn't go low enough, and therefore we say that there's no significant, or we couldn't make a conclusion, there's not enough evidence to reject the null hypothesis. But actually, if someone else were to carry out the same study better, maybe with more data, it turns out yes, they are different, there is a difference. So in this case, we had a false negative. We say that there's no difference when actually there is, right? And that would be a type 2 error, a beta error. Now, these two alpha and betas, we're using alpha, that's fine and all. But when do we use beta? We use beta when we want to calculate out our sample size, or statistical power calculations. And we might talk about that a bit in the future. Right? One last point I want to make is that we are actually only calculating statistical significance. Okay? Now, statistical significance is not the same as clinical significance. Statistical significance, you can find, given enough data, you can conclude statistical difference of tiny amounts. I'll give an example. Let's say you said that you wanted to give a conclusion as in what is the blood pressure, is there a difference in blood pressure between males and females, for example, right? Now, after collecting let's say 10,000 men and 10,000 ladies, you find a statistical significant difference. You're saying, yes, there is a difference between the population mean of men and the population mean of women, right? And we found out that that difference is based on, let's say, 5 millimeters of mercury. Now, 5 millimeters of mercury is peanuts. It's nothing. It's lost in the noise. So yes, there might have been statistical significance, but clinically, this finding has no significance whatsoever. So this one is based on real world. This one is based on the numbers. We are doing on the numbers, but make sure you never lose sight of the fact that those numbers still have to be translated into real world significance. Now, a quick note about statistical power. We're not going to go into too much detail into this because statistical power is mainly used in sample size calculations, and we don't usually do those by hand. Rather, we use statistical calculators for it. But still, you still need to know a little bit about this. Now, for power, if you remember alpha was the probability of incorrectly rejecting the null hypothesis when actually it is not incorrect. In other words, when actually the null hypothesis is true. Power, on the other hand, is the probability of rejecting the null hypothesis when it's false, meaning you're doing it correctly, of concluding the alternative when it is true. In other words, you got both. You get both conclusions correct. Right? That's statistical power, meaning the higher, the better, or analogous to sensitivity. Power in this case is 1 minus beta, beta being the alpha and the beta which we looked up previously. In practice, or in theory anyway, a power analysis is performed before a study to determine the sample size, required to detect an actual difference of some specified magnitude. As mentioned in the early times, when you do a sample size calculation, you're first required to set alpha values, then you're required to set beta values, or in other words, you're trying to give, say, I want my statistical test to have a power of 80% with an alpha value of 5, and I'm going to assume a difference of how much based on the assumption that my standard deviation of my population is so much and so forth, and based on all those assumptions, what is my appropriate sample size? Okay, so this only comes into play in power analysis or sample size analysis. And if you're interested in this, and you should be, if you're going to perform your research correctly, then go on and look for some statistical calculators online. Now, let's conclude with the question. We have learned two methods: estimation, which was using confidence intervals, or hypothesis testing, which was based on that two-tailed, one-tailed, etc., etc., etc. Now, why is it a question in the first place? It's a question because, honestly, in most scenarios, you can actually choose either to use estimation or hypothesis testing to come up with a conclusion. And both of them, for most questions, both techniques actually work, and they'll give the same answer, right? The same conclusion. Advantages, however, most people tend to use hypothesis testing because it is simple. There's a single value answer. Is there a significant difference? Yes, no. However, there are some disadvantages. There's a tendency to report only significance. Yes, there was a significant difference. No, there was no significant difference. And very often people kind of like omit, whether purposely or accidentally, on the magnitude of effect, meaning what was the actual p-value. There's a big difference between saying a p-value of 0.049 and a p-value of 0.00001. Right? The 0.049 could simply have been due to, if you carried out one more time, for all you know, you might have found no statistical significance after all. So it's a bit too crude, this report. It's also dangerous to make conclusions without studying the variability, right? It's roughly the same kind of thing. The confidence interval doesn't just tell you where you expect the mean to be. Just by looking at the range, you can also get some idea of saying, based on the data I have, it looks like the variability I have is a little bit too large to make any kind of useful conclusion from this. Even though statistically, if I convert to hypothesis testing, I might be able to give a statistical significant difference. But in terms of clinical practice, yes, it's significantly different, but the number may range all the way from here to there, right? Which might be more important than actually knowing whether it's significantly different or not, right? And because the confidence interval is a range, okay, then therefore estimation simply contains more information than hypothesis testing. Now, does this actually matter? Not really, right? Because in your exams, we will ask you to either use confidence intervals or hypothesis testing. I've never ever said a question that says, hey, you choose whether you use this or this. I'll just say use this or use this. So why does this matter? This matters in your own research or when you're writing papers to use this or this, frankly speaking, is up to you. Personally, hypothesis testing is actually fine to me as long as you specify the actual p-value that you got, or you specify the actual test statistic which you calculated, so people can make a conclusion for themselves how close it is to your alpha value, and so they have kind of have an indication of what was the magnitude of the significant difference. Right, with that, thanks.